So this here is the August 2017 Math 1151 second midterm. So what I will be doing is going through how to tackle some of these problems. Please note that the way that I solve the problems may not be the way you were taught to solve the problems or the way that you like to solve the problems. This is just meant to be an aid for you. And if you'd like to use my methods for problem solving, then you should feel free to do so. So for the first problem, it is said that f is the function with domain -1 to 6, just referring to the x values here. So we're going from -1 all the way to 6. So order the following four numbers from smallest to largest. The first derivative at -0.3, the first derivative at 0, the first derivative at 2.9, and the first derivative at 4. So I'm going to use four different colors here. Let me use blue, red, green, and yellow. I'm going to start with the blue, which is the first derivative at -0.3. We can estimate -0.3 to be about right there. And so the derivative there would look something like this. I'm going to call this a positive number, but it's not an incredibly steep slope. So I'll say here this is a small positive number. Remember, the derivative is just the slope of this line here. So it's definitely got a positive slope, but it's not incredibly steep like this. For the red one, that's the first derivative at 0. Well, the first derivative at 0 is going to be equal to 0 because our function is flat or nearly horizontal there. So we can assume that it is approximately equal to 0. The first derivative at 2.9, well, 2.9 will be something about right here. And our function at 2.9, if we draw a tangent line, that's a very positive slope. So I'm going to put here large positive. Keep in mind we read graphs from left to right. So from left to right, this line is going up very quickly. So it's going up, or much bigger than, the slope of this green line is much bigger than the slope of this blue line. And finally, for the yellow one, the first derivative at 4, well, we can see here's 4 in our derivative there. I'm hardly touching, if at all, but we can see that that derivative is a small negative. So from smallest to largest, we're going to start with f prime of 4, and that must be less than, let's see what comes next here. F prime of 4 is less than 0, which is f prime of 0. And next we have our small positive, which is f prime of -0.3. And finally, we have our large positive, which is f prime of 2.9. The next question asks us to list the critical points of f on the interval -1 to 6. List none if appropriate. Remember that critical points here refers to any x values, this is super important, that are in the domain of f, where f prime is equal to 0 or does not exist. So we just decided that the derivative was equal to 0. I'm going to highlight the spots where it's equal to 0. We just decided the derivative was equal to 0 at 0. Let me use green. So the derivative is definitely equal to 0 there. And I actually don't see anywhere else where the derivative is equal to 0. So I'm going to list here, I'm going to make a list, x equal to 0. That's where the derivative is equal to 0. Or we also have to find points where the derivative does not exist. So now we're going to go ahead and find those. derivatives do not exist at sharp turns, corners, cusps. So for example, right here, the derivative does not exist. And similarly, at 2, the derivative does not exist because we cannot draw a tangent line to this one point. Or in fact, we can draw a tangent line, but how many ways can you draw a tangent line to this one point? There are infinitely many tangent lines that can be drawn. So which one represents the derivative? Well, none of them. So we can say that this point, x equals 1, must be a critical point. So I'll go ahead and add it to the list, and I write it in blue because I highlighted those points where it doesn't exist in blue. So x equals 1 and x equals 3. I would like to point something out though. Let's say that this point 1, 2 did not exist in the original graph. Would 1 still be a critical point? The answer is no, because now 1 is not in the domain of our original function. There is no point at x equals 1. The function's discontinuous here, but beyond being discontinuous, the function doesn't exist at 1. There's no point. So if this point was not here, then 1 would not be a critical point. However, it is here, so we are going to include it as a critical point. Okay. List x coordinates at which f has a local maximum. So recall that local maximums require us to have a hill or a valley or a peak. So if you look at this graph here, we notice that, well, immediately what stands out to me is this point here, 1, 2, and also this point here, 3, -1. I will tell you only one of them is a local maximum, okay? And I'm going to tell you that it is 3, -1. So I'm going to go ahead and write this in blue because I already have it highlighted in blue. So x equals 3 is a local maximum, and that's actually our only local maximum. And the reason it's only x equals 3 is because in a small neighborhood around 3, meaning immediately to the left and to the right, our function exists, and 3, -1 is the highest point in that small neighborhood. So that might be a little confusing when you hear it that way, but let's go ahead and transfer that same vocabulary up here. At the point 1, 2, there is no neighborhood around this point. The graph doesn't exist to the left and to the right, so it has nothing to be bigger than, if that makes sense. So this point here is not a local maximum. It is an absolute maximum, meaning it is absolutely 100% the highest point on our graph, but it is not a local maximum. So I'm going to go ahead and cheat the system a little bit, and down here where it says absolute maximum, that is definitely x equals 1. And as far as a local maximum, it's just x equals 3. Now when it comes to local minimum and absolute minimums, there are actually none of these. And the reason is, if you were to tell me that, let's say, gosh, I guess we could use 1 again. If we go all the way down to meet our graph at 1, -3, first of all, our function doesn't even exist there because there's an open circle. So you might say, okay, well, what about 1.1? You know, what about this right here? Well, the truth is, if you say 1.1, I'm going to say, well, what about 1.0001? Something a little bit even closer. And if I say 1.0001, you might say, well, what about 1.00000001? Something even closer. You can always give a number, an x value, that has a lower y value. But the trick here is you can't say 1, because at 1, our curve does not exist. Well, it does exist at 2. That's the maximum. It doesn't exist down here at -3. So we can't use that. Similarly, at 6, -2, our curve doesn't exist. And if you think, well, what about 5.9? Well, what about 5.999999999? That's even closer. But you can always list a point that will have a lower y value. So for these reasons, there are no local minima, and similarly, there's not an absolute minimum. So here there are none. Let's move on to the next question. A function s is defined by the equation s of t equals t minus t squared for t between 0 and 5, including 0 and 5. S of t gives the position of an object moving along a horizontal line at time t, where s is measured in feet and t in seconds. Find s of 2 and mark the position of the object at the time t equals 2 on the line above. Well, seems like an easy question, right? S of 2 is equal to 2 minus 2 squared. That's 2 minus 4, which is negative 2. So this is S of 2. What I want to do first before we move on is calculate a few more of these values to see exactly how this particle is moving. So if we go ahead and we calculate 0, S of 0, S of 1, we already did S of 2, maybe I'll do S of 3, and how about an S of 4? Let's see what these give us. I'm just going to go ahead and plug them in my head instead of showing you the calculations. S of 0 is going to give us 0. S of 1 is going to give us 1 minus 1, which is 0. S of 2, we already decided, was negative 2. S of 3 is 3 minus 9, which is negative 6. And S of 4 is going to be 4 minus 16, which is negative 12. Don't know why I wrote this in black instead of green. So at time 0, we're at 0. Similarly, at time 1, we're also at 0. Interesting. At time 3, we're at negative 6. Oh gosh, so we're all the way back here, negative 5. We're all the way back here at negative 6. S of positive 3. And at time 4, we're at negative 12, so we're off the screen right now. So it looks like we are only moving backwards. We're starting at 0. We haven't moved, we're at position 0. Then at 1, we're at the same position. And then it looks like we're moving just to the left. But I'm really curious what's happening here between 0 and 1. So what I want to do is just pick another number. Let's just plug in 1/2. I'll plug it in black here. Let's just plug in 1/2 and see what happens. If we plug in 1/2, we get 1/2 minus 1/4, which is 1/2. Interesting. So here at 0.5, that is S of 0.5. So it looks like from 0 to 1/2, we definitely move forward, and then we move forward first, and then it looks like we start moving backward. So I wonder if 1/2 is the furthest forward that we move. I'm imagining that's the purpose of this problem, but let's find out. So at least now we have an idea of how this particle is moving. It's not just staying put from 0 to 1, it's going forward a little bit, then it's going backwards towards negative infinity. Well, because we end at 5, it's only going back as far as negative 20. So find the average velocity of the object over the interval 1, t. So average velocity would just be the slope of the secant line of this curve. So that would be something like, if you've seen this formula, f of b minus f of a over b minus a. And in the context of this problem, we have the function s. So here it would be s of t, or S of B minus S of A over B minus A. Now, our B and our A here are 1 to t. But one thing I want to point out first is that this gives us velocity because recall S of B is measured in feet. So when we do this difference here, we're going to get a measurement of distance, feet. And in the denominator, we have B minus A. Recall that these numbers here represent time. And here, that is in seconds. So we're taking the ratio of feet per second, and that's velocity. And we find average velocity, they just want us to find the slope of the secant line between those 2 points. So what we're going to do now is just plug in S of B minus S of A over B minus A. So here we'll say that A is equal to 1 and B is equal to t. So it's going to be S of t minus S of 1 over t minus 1. And I'm going to go ahead and do some algebra now. S of t is t minus t squared. And we already said that S of 1 is equal to 1 minus 1, which is 0, over t minus 1. So this gives us t minus t squared over t minus 1. I'm noticing in the numerator I can factor out a t, like this. And furthermore, I'm noticing that in the numerator I have a factor of 1 minus t, and in the denominator I have a factor of t minus 1. So if I factor out a negative 1 in the numerator, I'm actually left with the same factor in the denominator, leading these two factors to cancel out. And my average velocity is negative t. So the average velocity over the interval 1 to t is just negative t. I imagine if you were to leave your final answer in this form, that would also be acceptable. I really just enjoy simplifying when possible. So now we are being asked to evaluate the limit as t approaches 1 of the average velocity of t. So the limit as t approaches 1 of negative t would be equal to negative 1. Not much to it. The next question asks us, what does the limit in part C represent? Now, I'm trying to think of the best way to interpret this, if I were the person grading your exam, and what I imagine is being asked for here is for students to recognize that t is approaching 1, and in our interval up here, we have the interval from 1 to t. So if we put in here for t a value that's approaching 1, like say, 1.000001 or something really close to it, what we're actually doing now is not finding the slope of the secant line, but if we're getting dangerously close to 1, or if we're approaching 1, what we're actually doing now is finding the instantaneous velocity at 1, otherwise known as the derivative at 1. So I would say that this limit represents the instantaneous velocity at time 1. That's my interpretation of it. You could say, I suppose, negative 1 represents the average velocity as t approaches 1, but I kind of want to take it a step further and say that it does represent the instantaneous velocity, because here the instantaneous velocity, or the average velocity on 1 to t, is negative t, and if we replace t with 1, it's the interval from 1 to a number really close to 1, and that's the derivative. Again, I'm not a professor or teacher of this course in any way, but I imagine that's what's being asked for here. Next question says to find the velocity, not the average velocity, but the velocity v of t and the acceleration a of t. So what we need to know is that we have our position function, s of t, and then we have s prime of t and s double prime of t. The first derivative of position is velocity, and the second derivative of position, which is the first derivative of velocity, I should say, s double prime of t v prime of t is equal to a of t. So if the position function is t minus t squared, then velocity is going to be 1 minus 2t, and acceleration will just be negative 2. Okay, so determine when the object is moving to the right. To determine leftward and rightward movement, what we need to know that is if velocity is greater than 0, that means we are moving to the right. And similarly, if velocity is less than 0, that means we are moving to the left. Okay. You might ask yourself, what about acceleration? I thought it was acceleration. And the answer is when acceleration is greater than 0, we are speeding up. And when acceleration is less than 0, we are slowing down. So here we want to know when we are moving to the right, which means we're going to use this first concept here. When is the velocity greater than 0? And velocity is 1 minus 2t. So just some algebra here. When is 1 minus 2t greater than 0? Well, we can add 2t to both sides. 1 is greater than 2t. Divide by 2, divide by 2. We get here when 1/2 is greater than t. I like the variables being on the left for some reason. It's hard for me to interpret this. Or t is less than 1/2. So we are moving forward. Remember, I interpret moving to the right as moving forward. We are moving to the right when time is less than 1/2, which we saw in the beginning. I kind of got a lucky guess there in the beginning by choosing 1/2. But when time is less than 1/2, we are moving to the right. But for everything after that, our position function is taking us backwards. But if we plug a number in between 0 and 0.5, it's going to give us a number bigger than 0. We're moving forward. But then after 1/2, we turn around and we start moving backwards. So in this problem, we're given the graph of a function f, and we are asked about the inverse, the domain, and that's basically it. So first question says to find the domain of f, write your answer in interval notation. So we can see here that we have a vertical asymptote at x equals 2, which means that we will never, ever, ever touch 2. But we actually do touch 2 because we have this little point inserted here. So we do begin at 2, and in fact, we do end at 3. Even though we have an open circle here at 3, 0, at 3, -4, we do have a point. So in interval notation, our domain goes from 2 to 3. I'm using brackets because I'm including 2 and 3 in that. If we did not have these points there, if those points didn't exist, then I would write it like 2 comma 3 with parentheses. But those points do exist, therefore we are going to include them. Okay. Find the domain of F inverse. Write your answer in interval notation. So it's important to know that the domain of F is the range of F inverse, and the range of F is equal to the domain of F inverse. And we're being asked here for the domain of F inverse. So I'm going to go ahead and look for the range of F, because those two things are synonymous, just like the domain of F is synonymous with the range of F inverse. So let's go ahead and look for the range of F. Remember, range here refers to the y values that our function can take on. Range here is the y values. So our y values are -4, and then we don't take on anything between -4 and 0, and then we take on a y value of 0, and we go all the way up to positive infinity. So I would say our range is -4 in union with, well, I should not be using a parenthesis there, I should be using a bracket. -4 in union with 0 to infinity. Now I would like to note that I'm not quite sure of the proper notation here for just including 1 point, but our range only includes the point -4 and then 0 to infinity. So this is how I am choosing to write my final answer. But please pay attention to the very specific way your professors would like you to write this. F inverse -2 is what we're being asked for next. Now it's important to note that when we have F inverse of something, let's say, we'll just use here F inverse of -2, that's equal to something. We'll put a question mark. That's the same thing as asking the question, F of what thing is equal to -2. So what number do we plug into our function to get -2? Well, at a y value of -2, our function doesn't exist. So F inverse of -2 is not defined. Now, this next one says F of F inverse of 4. So that's like saying F, well, I'll rewrite the original thing here, of F inverse of -4 equals something, okay? But let's ask ourselves now, what number do we plug in to our function to get -4? That's what we're being asked for here. What number do we plug in to get -4? And we can see that we need to plug in an x value of 3 to get -4. Because this point's coordinates are 3, -4. So this question has now become not f of f inverse of negative 4, but it's now become f of 3, because 3 is actually f inverse of 4. So f of 3, when we plug 3 into our function, we get negative 4. We can see that this f and f inverse here kind of had a canceling effect on one another. But wait, you might be asking yourself or saying, hey, our question doesn't say negative 4. Our question doesn't say negative 4. But look, what I want to show you is I used negative 4 to show you that it comes out, the answer, to be negative 4, because this f and f inverse have a canceling effect on one another. Okay? So f of f inverse of negative 4 is negative 4, and we just went through the calculation here. Now here we're being asked for f of f inverse of 4. So this answer is going to be equal to 4. And this is the real answer to this question. But I want to point something out to you. If you tried to use the same logic that we used here, it's going to get very confusing. And here's why. If we look at f of f inverse of 4, we're going to be asking ourselves, what number do we plug into our function to get a y value of 4? And we see a y value of 4 is right here. So you ask yourself, what's the x value that you plug in to get a y value of 4? Maybe it's like 2.2, 2.25, 2.15. We don't know. And then you might go ahead saying, okay, well, it's probably like 2.15 maybe. And then you plug in 2.15 into your function, and then you're like, okay, well, f of 2.15 is, oh wait, that's 4. Isn't that what I just figured out here? Yes. This is why the f and f inverse have this canceling effect on one another. So what I'm saying is you don't need to estimate this number here, because we know that we're trying to figure out what this number is that gives us 4. So if we say it's 2.15, then we plug in 2.15 here, then we're saying, okay, what's the y value that we get when we plug in 2.15? Well, it's going to be 4. We just answered that question, but in the opposite direction. So the answer here is 4. And now the most challenging part of this is to sketch the graph of f inverse in the figure above, but hopefully I can make this a little bit simpler for you. When it comes to sketching the graph of f inverse, what we need to do is take every xy pair on our grid and flip it. I'm going to use 2 colors here to graph the inverse. I'm going to use red for my original function, and I'll use yellow for my new function. This point here is 3, negative 4. So to graph the inverse, I'm going to graph negative 4, 3. That's the first step. And we could have started with any other point that we knew the coordinates of. For my next step, I'm going to graph the inverse of this point. This point is 2, 0, so now I'm going to graph the point in yellow, 0, 2. Okay. Now you might remember from high school geometry that when you flip the coordinates like this, when you take an xy pair and you turn it into yx, this is a reflection over y equals x. So what we're doing here is reflecting these points over this line. And if you notice, the distance from this red point to this line of reflection is the same as this distance here. This line y equals x should be the perpendicular bisector of the line segment connecting our 2 points. See here, these are 90-degree angles, and this piece here is congruent to this piece, and this piece is congruent to this piece. So all we're doing is really reflecting our curve over the line y equals x. So if we continue reflecting these points, let's now take the point at 3, 0 and plot an open circle at 0, 3. Okay. And now let's take a point, say, that's all the points that we actually have, but let's take a arbitrary point, say, for example, the point here that's really, really close to 2, but just a little past it, let's say like 2.0000000000001, right? Just the next point after 2, it's so small we can't even count it. That's going to have a y value of like as close to infinity as you can get without actually getting there. So if you think of it like when you plug in 2.000 yada 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 1, you're going to get something really close to positive infinity. So now we're going to reverse that. And if we reverse that, it's going to give us, when we plug in an x value of something really close to infinity, we're going to get a y value of 2.000 yada yada 1. So if you think about positive infinity as an x value, that's going to be all the way out here and at a y value of 2.000000001. So that point is like right here, and that's just a very, very poor estimate, I'm sure. You know, it's not perfect. And what we can do now, because we have these 2 points, is we could kind of connect them, you know, and this would, I could draw an arrow, but I'm just going to go out here and connect it here and then draw an arrow. And while this is not perfectly done, my curve is not perfectly drawn, you can see that if I connect these 2 points, I actually have the perpendicular bisector again. So yeah, I hope that made sense. If not, leave a comment and I'll be happy to reply. So in this question, we're given f is a differentiable one-to-one function with domain 0, 6, with the particular values of f and f prime given in the table below. F inverse is the inverse function of f, and g is the function given in the graph. It looks like an upside-down parabola, and then it turns linear. So, first question says, find the value, or write, not to find, show your work. The first one here is the limit as x approaches 5 of g of x minus g of 5 over x minus 5. Please note that this is the limit definition of the derivative. This is the limit definition of the derivative. Derivative. Oh my gosh, I cannot spell right now. Derivative. You get the idea. Okay. So, I'll just write it. Derivative. There we go. So there are 2 ways to write the limit definition of the derivative. It could be the limit as x approaches c of f of x minus f of c over x minus c, or it could be the limit as h approaches 0 of f of x plus h minus f of x all over h. And what we have here is an example of this. And what I hope you notice is that our c value is 5. So, how do we do this? Well, this first question is just asking us, what is the derivative at x equals 5? Or another way to put it is, what is g prime of 5 equal to? We say that this here is a linear function, right? This here is linear. So if you think about a linear function would take on the form y equals mx plus b. So if we want to know the derivative at any point on this line, we would need to know the derivative of the line, which would be, well, the b is a constant, so that goes away. And here, the derivative of mx would just be m. So the derivative is just going to be equal to the slope of that line. So what we can do now is calculate the slope of this line. We're going up 1, over 1, up 1, over 1. So the slope of this line is equal to 1. Therefore, the derivative is equal to 1. I want to show you now, though, another way to tackle this problem. So I'm going to go ahead and erase what's here on the side. I want to show you another way to tackle this problem. Let's say you didn't know that, and you were just like, what? How do I solve this? If you're familiar with this thing called L'Hopital's rule, it allows us to simplify limits when we get indeterminate forms. And one of the indeterminate forms that we might get when doing limits is 0 over 0. Minus. So if we plug in 5 here, if we were to plug in 5, we get g of 5 minus g of 5 over 5 minus 5, which is 0 over 0. Now we're allowed to use L'Hopital's rule, because what we got was 0 over 0 in indeterminate form. So L'Hopital's rule allows us to take the derivative of the numerator and the derivative of the denominator and then evaluate the limit again. So we can say the limit as x approaches 5, and I'll put equal signs here, and every time I use L'Hopital's rule, I always put an H just to signify that I am using that rule. That's how I got to this step. That would be g prime of x minus, well, what's the derivative of g of 5? G of 5 is equal to 1, and the derivative of 1 is equal to 0. So I'm just going to put 0 there, because g of 5 represents a number. It represents an integer, it represents 1, and the derivative of 1 is 0. So I'm going to put a 0 there. Over the derivative of x minus 5. The derivative of x is 1, and the derivative of 5 is 0. So what I'm left with is the limit as x approaches 5 of g prime of x over 1, which is just the limit as x approaches 5 of g prime of x, which is g prime of 5. The derivative at 5, we just decided the slope of that line is equal to 1. So if you didn't know that was the limit definition of the derivative in the beginning, you could still use L'Hopital's rule to solve this problem. Okay? All right, let's move on to the next one, but first I'm going to go ahead and erase this work here. All right, next one is asking us to find the derivative of this product of functions here. So what we're going to use here is the product rule. A very watered down version of this that says if you want to do the derivative of a function times another function, that's the derivative of the first function times the second one left alone plus the first one left alone times the derivative of the second one. So f prime g plus f g prime. So we have here two functions, color code blue and green. Okay, So the derivative of the first function, derivative of the first function is going to be g double prime x plus 2. Notice that there's nothing attached here to the x, but if it were like, say, 5x, I would need to put the derivative of this thing on the outside. So if you want me to, I could still do that actually. It would just be 1. That's the derivative of what's on the inside. And then we're still going to multiply that by the other function left alone, which is f of x, just stays f of x. And we're going to add to this the, I have to erase, I gotta get better at my spacing here. We're going to add to this the first function left alone, so g prime x plus 2 times the second function's derivative, which would be f prime of x. Now we're gonna go ahead and evaluate at 3. G double prime of 3 plus 2 times f of 3 plus g prime of 3 plus 2 times f prime of 3. And this simplifies to g prime of 5. And over here we also have, I'm sorry, g double prime of 5, and over here we have g prime of 5. Now you might be asking yourself, how do I find g double prime of 5? How do I find this? Well, we know g of 5 is equal to 1. And we know that the derivative at 5 is also equal to 1. Now the second derivative always tells us concavity. It's a measure of the rate at which something is growing, okay? So when I think of second derivative, I think about parabolas. Like, I would say that this shape here is concave down because our tangent lines to this curve all lie on top. Right? It's all of our tangent lines lie on top. So that's concave down. Similarly, a parabola that was opening like this would be concave up because all the tangent lines lie below. So when you have a line like this, where's the concavity? Like, is it concave up or is it concave down? And I look at that and you know what? I don't see any concavity. It's neither concave up nor concave down. So the second derivative at 5 is equal to 0 because it's neither concave up nor concave down. So the fact that that's equal to 0 eliminates this whole thing because we're multiplying it all by 0. Plus the first derivative at 5, we decided earlier that was equal to 1. That was in the first part of the question. We decided that was equal to 1 times f prime of 3. Now for f prime, we have to go back and look at this table here. The first derivative at 3 is equal to 2. 1 times 2 is equal to 2. And that's our answer. So for the next part C, we're being asked to find the derivative of the inverse at 2. So one important rule we need to know is that when we want the derivative of the inverse, or f inverse of x prime, that's the same as 1 over f prime f inverse of x. Okay, so in the denominator, I know when it comes time to an exam, you might think, wait, is it f prime f inverse or f inverse f prime? I remember it as first prime, then inverse pi pi or private investigator, whatever works for you. But if you want f inverse prime, do 1 over f prime f inverse of x. So here we're going to, in order to find f inverse of 2 prime, that's equal to 1 over f prime f inverse of 2. And remember, when we want to find f inverse of 2, when we want to find f inverse of 2, that is asking us what number do we plug into our function? What number do we plug into our function to get to as an answer? So we're going to go ahead, back up here and look at this table. I'll eliminate all the green that I put on there. And now keep in mind, we're not plugging in f of 2. That's not what we're doing. Okay, what we're doing is we're saying what number do we need to plug in order to get 2 as an answer? Well, 2 is an answer here. And what did we plug in to get 2? We had to plug in 1. So what this is going to be equal to is 1 over f prime of 1. Because f inverse of 2 is synonymous with the number 1. Okay? And now what we have to do is 1 over f prime of 1. And from the table we can see f prime of 1 is 4. So our answer is 1 over 4. Now for this last one, I'm going to need a lot of space, so I'm going to try to, you know what, there's not much space at the bottom of this page, so I'm just going to erase my work above. And if you'd like to still copy it down, please pause. Okay, so for this next one, I'm going to need a lot of space. I'm not joking, so let me give myself some more space here. I'm just going to copy the problem nice and big over here. We want to find the derivative of x to the power g of x at x equals 2. So there might have been a fancy rule you learned for solving these problems, but I think about them, I don't really have anything memorized to take this derivative. I just approach it as logically as possible. I'm thinking if we have this function y equal to x to the power of g of x, I want to find the derivative of this function, right? So I know the derivative of the left side. Well, actually first, you know what? I don't like that g of x being in the exponent. I don't like that up there. I want to get rid of that. It makes me anxious as hell. So let me take the natural log of both sides. But on the right-hand side, when I have a natural log and I have an exponent like this guy actually comes out in front. That's a property of logs. Now this feels much more workable because what I have on the right-hand side now is just a product rule. That's it. G of x times natural log of x. So let's start now taking the derivative. On the left-hand side, the derivative is going to be y prime over y. Remember, as an aside, if you have the natural log of f of x and you want to do the derivative, that's going to be f prime of x over f of x. So here it's y prime over y. And now that's equal to, let's go ahead and do that product rule. We have our g of x and we have our ln of x. Our g of x derivative is going to be g prime of x times natural log of x plus the g of x left alone times the derivative of the natural log of x. What goes on the bottom is the thing inside the log. What goes on the top is the derivative of that thing, so it's 1 over x. But now we just want the derivative y prime. We don't want y prime over y. This right now is bad over here. We don't want all of that. What we want is just this thing on top, y prime, the derivative. So what we have to do is get rid of that y on the bottom, and we can do that through multiplying both sides by y. Because if I multiply by y on the left-hand side, those y's cancel out. If I multiply by y on the right-hand side, I'm good. So what I have now is that y prime is equal to, let's see here, we got g prime of x times the natural log of x plus g of x times 1 over x, and we're not done yet, times y. What is y? Well, let's go all the way back up to find what y is equal to. We have this equation here. Y is x to the g of x power. So it's times x to the g of x power. Now you might think we're done. We sure as hell are not, because now we have to evaluate. Y prime equals bracket or parenthesis, whatever, g prime of 2 times natural log of 2 plus g of 2 times 1/2 bracket, plug in, x is 2 to the g of 2. Holy cow, we are almost done. Let's figure out what all these things are equal to now. Put the 2 there. G prime of 2 we can find from looking at our graph. And remember, g prime of 2 means the derivative of g at 2. So if we go back to our graph of g of x, the derivative at 2, the tangent line at 2 is horizontal, which means the derivative is equal to 0. So actually, because this thing here is equal to 0, all of this is just going to cancel out because we're multiplying by 0. Great, moving on. G of 2. G of 2, not the derivative, just g of 2 is equal to 2. So this thing here, g of 2 is equal to 2. Let me write that in blue. And then we're multiplying that by our green 1/2. And then that's it for everything inside the brackets. On the outside, we have 2 to the power of g of 2. And we just said that g of 2 is equal to 2. So it's 2 squared. So what we have here is 2 times 1/2. This is equal to 1. Outside the brackets, we have 4. All of that work to get 4 as our answer. So the answer here is 4. Cool. So in this problem, we're given the curve tangent inverse of y plus x plus y times the natural log of x minus 1 is equal to 2. And we are being asked first to find the implicit derivative of this equation. So one thing I want to point out to you first is that we are asked to find things implicitly, or derivatives implicitly, when our function contains y's and x's, and the y's cannot be isolated. For example, if we had 4x equals y plus 2, we do not need to do this implicitly because we can get y by itself isolated explicitly alone. However, if we have 4x y squared plus y equals 9, now getting y isolated explicitly would be quite the feat. So we would do this derivative implicitly. So this one here would be explicit, whereas this one would be implicit. Notice that we have this y and this y, so we're going to do the derivative implicitly. Now in single variable calculus, you were taught that if your function f of x is equal to, let's say, x squared, we're taught that the derivative would be 2x. The derivative is actually 2x dx dx, or the derivative of x with respect to x, but this is a ratio equal to 1. So we don't really write dx over dx. Now if our function is in terms of y, our derivative would be 2y dy dx. Now here, our ratio is not equal to 1, therefore it doesn't cancel out. It's not equal to 1. So we can't forget about it. So we're going to go ahead and take this derivative piece by piece. Tangent inverse of y plus x plus y times the natural log of x minus 1 is equal to 2. Now, the derivative, we'll start with the easy pieces, so to speak. The derivative of x is going to be 1, and the derivative of 2, be careful, is 0. Moving forward, we want to find the derivative of tangent inverse of y. The derivative of tangent inverse of y is going to be dy dx over 1 plus y squared. Now let me show you where that came from. It's a bit of a chain rule thing happening here. Let's say we had the derivative of tangent inverse of 2x. Let's say 2x squared. The derivative of this, well, it's kind of like the chain rule. We want to first derive tangent inverse. And the derivative of tangent inverse would be, let's say this here is our function f. The derivative of tangent inverse would be 1 over 1 plus this angle, whatever it may be, squared. So 2x squared squared. So whatever this angle should be here goes in the denominator. Now in the numerator, we must multiply by the derivative of that angle. So our angle was 2x squared. The derivative of that angle is 4x to the first power. So that gives us f prime is equal to 4x over 1 plus 4x to the fourth. So here, our angle is y. So in the denominator, this is why we have y squared. In the numerator, we have the derivative of y, which is just dy dx. Plus 1, plus, now we're going to use the product rule here. We must use the product rule because we have two functions being multiplied together. So, the way the product rule works is we do the derivative of the first term, which is dy dx, times the second term left alone, natural log of x minus 1. I'm going to create some more space for myself here. Plus the first term left alone, which is y, times the derivative of the second term, which would be 1 over x minus 1. And all that's equal to 0. Now, if you're not sure where that natural log derivative came from, remember, and I believe I did this earlier in this tutorial, in this video, when we have a natural log derivative, such as this. So when we have natural log of x minus 1, if this is our function f prime would be the derivative of the natural log. Again, this is another chain rule. So the derivative of the natural log function is 1, I always write in the highlighter, 1 over the angle, which is x minus 1, or 1 over the quantity, I should say. 1 over the quantity times the derivative of the angle, of the quantity. So the derivative of x minus 1 in this case would just be 1. Okay? So that's just equal to 1 over x minus 1. Now, this here actually does not simplify too nicely. So what I'm going to do now is a few things, but I'm going to skip through some steps because it's just algebra. I'm going to move this term and this term over to the other side of the equation. And the reason I'm doing that is because the objective here is to isolate dy dx. The objective here is to isolate these two terms. So I'm going to start by moving everything away that has nothing to do with those two terms. So I'm left with dy dx over 1 plus y squared. Then I have this plus dy dx times the natural log of x minus 1, and that's equal to, I'm going to put everything else in black over here, minus 1 minus y over x minus 1. Okay, all I did was move stuff to the other side of the equation. And now I'm going to factor out a dy dx. So I'm going to take this thing here and this thing here and pull it out, just like you would do if you had, 2x plus 4x squared plus 8. We can factor out from this a 2 and leave it as x plus 2x squared plus 4. I took out the 2 because all of them have a 2 in common. So here I'm going to take out a dy dx. So now I'll turn all to black. That leaves me with dy dx times the quantity 1 over 1 plus y squared plus the natural log of x minus 1 equals negative 1 minus y over x minus 1. I'm going to create some more space for myself. Oops. Okay. Now I'm just about done. I'm going to divide both sides now to isolate the dy dx. That leaves me with dy dx equals negative 1 minus y over x minus 1 over the quantity 1 over 1 plus y squared plus natural log of x minus 1. And again, all that I did here was divide both sides by this big messy term. Okay, so I did it. I isolated dy dx. And our final answer is all of this. Okay. The next question says, verify that the point 2, 0 lies on this curve. Well, pretty easy question after all that hard calculus. X is 2, y is 0. So that means when I plug in an x value of 2, I should get a y value of 0. So if I go back up here to my equation, I'm plugging in y equals 0. I'm plugging in x equals 2. I'm plugging in y equals 0. I'm plugging in x equals 2. Tangent inverse of 0, if you plug that into a calculator, or if you know your unit circle, that's going to give you 0. Plus 2 plus, well, 0 times anything is 0. And look at that. We get 2 equals 2. Great. Part C, so we're done with part B. We did part A. Now we're on to part C. A part of the curve that contains a point 2, 0 is shown in the figure. In the figure above, draw the line tangent to the curve at the point 2, 0. So if we're drawing a tangent line, one thing I want to point out is that we really need to know the slope of that tangent line. Like, I can envision that it's going to look something like this, but I want to make it as accurate as possible. So what I want to do is find the slope of the tangent line at 2, 0. And to find the slope of the tangent line, we need the derivative. But guess what? We already found the derivative. This here is the derivative. So what I'm going to do is I'm going to go ahead and calculate the slope of this tangent line by plugging it in. Realistically, they should have asked you to calculate the slope of the tangent line already. This seems a bit backwards, but let's go ahead and substitute. So we have -1, so the slope of the tangent line dy dx is equal to -1 minus my y value is 0 over my x value, which is 2 minus 1, and all of that goes over 1 over 1 plus y squared, which is 0 squared, plus ln of 2 minus 1, and this here is a squared. So if I do all of this simplification, if you were to go about this carefully, you would get -1 over 1, which is equal to -1. So the slope of the tangent line is -1, which means we go down 1 and over 1, down 1, over 1. So our tangent line is going to be the connection of these 4 points here. Oops, apologies. Our tangent line will be all 4 of these points connected. That was not the smoothest line drawing. I think my first line that I drew looked better. And there I hadn't even known the slope. So let me try this one more time. It's not the sexiest line I've ever drawn, but whatever. Okay, so this line has a slope of 1. Okay, so we did part C. We drew the tangent line. Okay, part D. Find the slope. Oh, well, we just did that. The slope is equal to 1. I feel like they should have asked you for this first. Who knows? Okay, write an equation of a line tangent to the curve at the point 2, 0. So equation of any line, I'm going to use here point slope form. Y minus y1 equals mx minus x1. I'm realizing now I wrote the slope as 1, but the slope is -1. My apologies. So our y value that we've been using is 0, and our slope that we just found was -1, and that's x minus 2. So this gives us y equals -x plus 2 after simplification. That means our y-intercept is 2, and that looks correct. Keep in mind here, this is not the origin, so this is not the y-intercept. If we went over 1 more and up 1 more, our y-intercept would be 2, and we would be at 0, because here we're at 1, we go back 1 more, we're at 0, up 1 more, we're at 2, that's our y-intercept. Okay? Hope this problem made sense. Leave comments if you need more assistance. Thank you. This last problem, we're given an isosceles triangle with 2 sides of length s, measured in feet, and the base of length 6. A is the area of the triangle. So because we're talking about area, I'm just going to remind myself, area of a triangle is 1/2 base times height. So in this case, area is 1/2 times 6 times height. Okay, part A says label the figure above. Well, we did that. Perhaps they want us to be specific here. I can put the symbol for feet, S feet, 6 feet. And then we just jump right into a related rates problem. At what rate is the area A of the triangle changing when A is equal to 12 square feet? So what we want to do here is find out how quickly the area is changing. And we've introduced this element of time now. We have here S is increasing at a rate of 4 feet per minute. That means the rate at which the side length is changing with respect to time is 4. And I know it has to be dt with respect to time because, again, we have this introduction of time here. So now what we need to do is derive the area formula with respect to time. This actually all simplifies to 3h. Area is equal to 3 times the height. But here's the thing. We don't know what the height of the triangle is. So what can we do? Well, we can think geometrically here. If we draw a perpendicular line from the vertex of the isosceles triangle to the base, we can find this missing side using the Pythagorean theorem. So we know that the hypotenuse squared, let me erase that. We know that the hypotenuse squared, which is S, is equal to 3 squared plus height squared. So we know that S squared is equal to 9 plus h squared. And so S squared minus 9 is going to be equal to h squared. So h, the height, is just going to be the square root of this. So h is equal to the square root of s squared minus 9. So what we can do now is label this height as the square root of s squared minus 9. Okay? And now what I'm going to do is make this substitution into our area formula. So I know area is equal to 3h, but now I also know area is equal to 3 s squared minus 9 to the 1/2. So now I'm going to take the derivative of this equation with respect to time, knowing that dA dt is what I'm looking for. ds dt is equal to positive 4. Area at this moment is equal to 12. And S, well, we'll talk about that in just a moment. So I'm going to derive both sides of this equation with respect to time. Remember, area, the derivative of area with respect to time would be dA dt. And here I just use the chain rule. This gives me 3 times 1/2 times s squared minus 9 to the negative 1/2 times 2s, and the most important part, we cannot forget this, times 2s ds dt. Right? The derivative of 2x with respect to x would just be 2. And again, it would be dx over dx, but that cancels out. If we're deriving s with respect to time, the derivative would be, or 2s would be 2 ds dt. So here we have s squared, the derivative is 2s ds dt. Okay? So now we can go ahead and substitute our values. dA dt is what we're looking for, so we're not going to substitute anything there. 3 halves. We have to find what the value of s is. That's interesting. And then we're plugging in s there, and ds dt we know is 4. So let's talk about s, okay? S, which I was using blue for, s represents the side length. So we have to evaluate, we have to plug in a number for s in all of these spots, okay? So how do we know s? All we know, all that we have is this information over here. We were also given, remember I erased it, that area is equal to 12 at this moment in time. So if the area is equal to 12, what is the side length? Okay, so follow me back up here. If area is equal to 12, that means 12 is equal to 1/2 times base times height. We know the base is 6. So that means 12 is equal to 3h divided by 3 divided by 3. That means that the height is equal to 4. So the height is equal to 4. Is that the value of s? No. S represents the side length, not the height. So if the height is 4, what I can do now is take this 4 and substitute it in for the height. Right? You could plug it into this equation and solve, or you could plug it in down here and solve. Right? If you know that s squared is 3 squared plus 4 squared, then using the Pythagorean theorem, that's a Pythagorean triple. 3 squared plus 4 squared is 25. The square root of 25 is 5. So this means that s at this moment in time is equal to 5. So if I put this square back that I accidentally erased, and if we were to evaluate all of this, dA dt equals, this would be 3/2. 5 squared minus 9, 25 minus 9 is 16. It's to the negative 1/2, which means we're going to do 1 over the square root of 16, which is 1 over 4. 2 times 5 is 10 times 4. So what happens here is that a lot of these things cancel out, right? 4 and 4, then the 2 becomes a 1, and the 10 becomes a 5. And what we're left with here is 15, and we're going to put that in 15 square feet per minute is the rate at which the area is changing. Okay? So, if you have any questions on this video, you should feel free to comment, and I'd be happy to answer them. Otherwise, please like my video, and if you would like me to do more of these videos for more practice exams, I would really be happy to do so. So let me know your thoughts. Please share the video with your classmates in this course if you think that they might benefit from it. Otherwise, it was my pleasure doing this, and I hope that you found it helpful in preparing for your next calculus exam. Thank you so much for watching. Bye-bye.